Hello and welcome to the next program of network analysis. This program introduces some another important fundamental network theorems of network analysis, which are the source transformation, Norton's theorems, maximum power transfer theorem, Millman's theorem and reciprocity theorem. We will discuss all the theorems one by one in details in this program. Let us start with the source transformation. Source transformation theorem states that we can convert any voltage source into the current source and vice versa. We know that all the real voltage source have the internal resistance in series and all the current source have the internal resistance in parallel. So, by using just Ohm's law, we can get the voltage from the current by keeping the same resistance, that means the resistance remains the same, by multiplying the current and the value of current source by just dividing the voltage by that resistance. So, we can convert a voltage source in the current source and current source into the voltage source by using this theorem. Next is our very important theorem, Norton's theorem. In the last program, we have learned that any complicated network have its equivalent voltage source circuit. Now, the equivalent current source circuit can be determined by using the Norton's theorem. So, Norton theorem states that a linear two-terminal circuit can be replaced by equivalent circuit consisting of a current source IN in parallel with a resistor RN, where IN is the short circuit current through the terminals and RN is the input or equivalent resistance at the terminals when all the independent sources are turned off. So, Norton theorem gives us a current source equivalent circuit in which we have a current source of value IN and a parallel resistance RN, that is in shunt resistance RN is connected with this source. Now, how to find the Norton equivalent circuit? As we know that this is very much similar to the Thevenin theorem, so there are very similar steps like the Thevenin theorem. So, proving this Norton theorem, we have taken the same circuit as we have taken it in the last program for the Thevenin theorem. So, step 1 is that remove the part load of the network across which the Norton equivalent circuit is found. So, in this circuit again we will remove the load and open the terminals A and B, for which we have to find the current. Now, the next step is that we have to find the Norton resistance, that is RN. The resistance RN can be found with the same procedure as we find the Thevenin resistance. So, we have to remove the given source by its internal resistance. So, here we short the voltage source and the resistance across the terminal A and B looking from these terminal is the RN. So, RN, here we get the RN as R2 plus the parallel combination of R1 R3 as we get in the Thevenin theorem. So, we can see that RN is equal to the RTH. The next we have to find the Norton current. As we discuss it in the statement of theorem, that the Norton current is the short circuit current flowing from the terminal A and B. So, for finding the Norton current, we place a short across the terminal A and B, and now the current flowing from this short circuit terminal is the Norton current. So, here we can find the Norton current by using just the current division law, but for finding IN we have to find first of all the total current I. So, here we can see that I is given here and we can find it directly by using the Kirchhoff law. So, we can say that our assumption for the Norton theorem is true, and we can convert any complicated network into its equivalent current source circuit. In the last, we can conclude that Norton theorem is the converse of Thevenin's theorem. It consists of an equivalent current source instead of an equivalent voltage source as in Thevenin theorem. The determination of internal resistance of source network is identical in both the theorems. Again, we can transfer a Norton equivalent circuit into the Thevenin equivalent circuit by just using the source transformation theorem. As we know that voltage source converted into the current source by just using the Ohm's law. So, we can convert a Thevenin equivalent circuit into a Norton equivalent circuit and vice versa. This is essentially a source transformation and known as the Thevenin-Norton transformation. Now, we can understand the procedure of finding the Norton equivalent circuit by just taking this example. Here in this example, we have to find the current in the given load. So, first of all, we will remove this load and open the terminal A and B. Then for finding the resistance Rn, we will remove the voltage source and replace it by a short circuit. Now, we can see that Rn looking from the terminal A and B is nothing but the parallel combination of R1 and R2. And next, if we want to find the Norton current, we will place a short circuit across the terminal A and B. Now, we can see that resistance R2 and the short circuit become parallel to each other. So, the resistance R2 will be replaced by the short circuit. Now, we can see the short circuit current, that is the Norton current, is nothing but the ratio of voltage to the resistance R1. So, the value of IN we get is 3 ampere. Here we have the Norton equivalent circuit. So, IN is equal to 3 ampere and Rn is equal to 2 ohm. Now, we reconnect the load resistance across the terminal A and B again, and we can find easily the IL current. Again, we can convert this Norton equivalent circuit into the Thevenin equivalent circuit, as the value of Thevenin voltage is the product of IN Rn, that is 3 ampere multiplied by 2 volt ohm is equal to 6 volt. Now, in the last, we can say we can convert any complicated network into its current equivalent circuit, and then we can again convert into the Thevenin equivalent circuit, or if we get directly the Thevenin equivalent circuit, we can convert it into the Norton equivalent circuit. Next, we will discuss about the maximum power theorem. But before discussing this theorem, we have to know the concept of power. Power is the time rate of expending or absorbing energy, and it is measured in watts. It is the joules per second. As we know that power is the time rate of energy, but the electrical power can be defined as the product of voltage and current across any terminal. So, the circuit element that absorbs power have a positive sign and that produces power have a negative sign. So, we can say we have two types of power, and we can find this the sign of power by the passive sign convention. If we have to given any circuit, we know we can make its voltage equivalent circuit. Now, if we want to connect a load for which we want to get the maximum power, then what should be its value? As we know, if RL is 0, then we get the maximum current, and if the RL is infinite, that is the RL is have its maximum value, then we get the maximum voltage but no current. In both the extreme cases, we get the load power as 0. So, we want to know the value of load for which we get the maximum power. Thus, the aim of the maximum power transfer theorem is to determine the value of load resistance RL such that it receives maximum power from the DC source. And a variable resistance RL is connected to a DC source network can be represented as the Thevenin voltage VTh with the series Thevenin resistance RTh of the source network. So, the maximum power transfer theorem states that for loads connected directly to a DC voltage supply, maximum power will be delivered to the load when the load resistance is equal to the internal resistance of the source, that is when load is equal to the R internal resistance, we get maximum power across the load. And we know we can convert any network into its Thevenin equivalent network. So, if we convert the network into the Thevenin equivalent circuit, then the internal resistance will become RTh. Thus, we get the maximum power for load when it will equal to the Thevenin resistance, that is RTh. Now, we have to prove the maximum power transfer theorem. Here we have taken a Thevenin equivalent circuit. So, we have a voltage source VTh with the series resistance RTh, and then we have connected a variable load resistance. Now, easily we can find the current flowing from the load from the equation 1, and the power delivered to the load can be found by the I square RL, and that is given by the equation 2. Now, if we plot a graph between the varying value of RL with the varying value of load power, then we get this graph like as shown in the figure. So, we can say we get the maximum power when RL is equal to the RTh, and we can see we get the peak for this value. As the RL is less than RTh, the power is decreases. Similarly, as the RL is greater than RTh, the power is again decreases from its maximum value. We can prove it by theoretically, as we know we get the peak at this value. So, we can say we get the value of maximum power when the derivation of power with respect to RL become 0, that is dPL upon dRL is equal to 0. So, differentiating the equation 2 with respect to RL, we get this equation, and equating it equal to 0, as we want to get the maximum power for this. By solving this equation, we get that we get the maximum power when RL is equal to RTh. So, our assumption for maximum power theorem becomes proof, and we get the maximum power by substituting the value of RL equal to RTh in equation 2, that is equal to VTh square upon 4 RTh. So, we can say that at best we get the maximum power, that is the 1/2 of the all over power. 1/2 of the power is dissipated in the internal resistance, and another half power which are we getting across the load. Next, we have to find the Thevenin equivalent voltage. Here we can see that we have two sources, so we can use the superposition theorem here. So, first of all we will consider the voltage source alone, and we will find the voltage across the terminal AB. So, first we will find VAB1 due to the voltage source, and we can find it directly by the voltage division law, and we get 3.75 volt. Next, we will consider alone the current source as shown in figure, and we can find this voltage VAB2 is equal to 7.5 volt. Now, the total voltage becomes 11.25 volt. So, the Thevenin voltage is the summation of VAB1 and VAB2. Finally, we get our Thevenin equivalent circuit. Here the ETH is 11.25 and RTH is 1.5 kilo ohm. So, we have to keep the value of RL is equal to 1.5 kilo ohm for getting the maximum power across it, and then the maximum power can be find by just using the equation VTH square upon 4 RTH. Next is the Millman's theorem. By using the Millman theorem, if there are several voltage source connected in parallel branches, then we can find a single voltage or common voltage for these voltage sources by using the Millman theorem. Although we can find it by using any other theorem, but Millman theorem gives the straight and very direct and simple equivalent circuit. Thus, the Millman theorem states that any number of parallel voltage sources having internal resistances differently can be reduced to one single equivalent voltage source V in series with an equivalent series resistance R. This theorem is given by Jacob Millman, and it is applicable only to solve the parallel branch with one resistance connected to one voltage source or current source. So, we can use Millman theorem only for those circuits which have several parallel connected branches containing a voltage source and series resistance, current source and parallel resistance, and the combination of both. Here we have some steps for solving any circuit by using the Millman theorem. In this figure, we have 3 n voltage sources with their internal resistance, and we have to find its equivalent single voltage source. So, first of all, we will convert all the voltage source into the current source by using the source transformation theorem. So, we get this equivalent circuit as shown in figure, in which we have all the current sources are connected parallel. Now, we get a single current for all the sources by just adding them. So, we get equivalent current by algebraic sum of all the parallel currents. Next, we can find the equivalent resistance or the equivalent conductance by just adding all the conductance, and which is equal to the reciprocal of equivalent resistance, that is GEQ is equal to 1 upon REQ. So, finally, we get a equivalent current source circuit for several parallel connected voltage source. Now, we can convert this current source equivalent into the voltage source equivalent by using the source transformation theorem. So, finally, we get the equivalent voltage as IEQ multiplied by REQ, or we can directly find the equation for finding equivalent voltage source, that is, we know that voltage equivalent is nothing but the ratio of current with the conductance. So, all the current can be write as the ratio of voltage to resistance, and all the conductance can be write as the reciprocal of resistance. So, finally, we get the equation for V equivalent is V1 upon R1 plus V2 upon R2 plus V3 upon R3 divided by the sum of all the reciprocal of resistances. By this example, we can understand the use of Millman's theorem. Here we have given the 3 sources in which one is current source and 2 is voltage source. Now, first of all, we will convert this voltage source into the current source as shown in figure B, and finally, we get the single current by adding them. So, we get value of current is 4 ampere. Now, we can find the equivalent resistance by connecting parallel them. So, we get it 2 ohm, and then we can convert this equivalent current source into the equivalent voltage source by multiplying 4 to 2. So, we get our voltage source equivalent circuit as calculated in by these equations. We can find it directly by using the formula. So, we have the current as 5 plus 12 by 4 minus 24 by 6, and then we can find the equivalent resistance by connecting them parallelly as 1 by 12 plus 1 by 4 plus 1 by 6, and we get the same value of voltage and resistance as we get in the previous procedure. Last is the reciprocity theorem. The reciprocity theorem is applicable only to single source network. So, we can say that we can use it for only those circuits which have a single source. It states that any linear bilateral network, if a source of EMF E in any branch produces a current I in any other branch, then the same EMF E acting in the second branch would produce the same current I in the first branch. So, we can say that reciprocity theorem states that we can interchange the location of voltage and the resulting current with each other without affecting the circuit. In simple word, the location of the voltage source and the current source may be interchanged without a change in current. However, the polarity of the voltage source could be identical with the direction of the branch current in each position. So, it simply means that E and I are mutually transferable. So, here we have taken a circuit in which we can say, by using this circuit we have to prove the reciprocity theorem. So, firstly we choose the branch where we have to find the current due to this given voltage source A. So, we place a ammeter in that branch which is given by the symbol B. So, first we will find the current in the given situation, that is we keep the circuit remains as it is and we find the current in the meter B, and by calculating using the simple Kirchhoff law we can find that current, and this is equal to 3 ampere. Now, we will interchange the meter and the voltage source, that means the current comes at the position A and the voltage source goes to the position B, and then we will find again the current in this figure or in this situation. So, again calculating these current by simply using the Kirchhoff law, we get it again 3 ampere.